Hi everyone and welcome back. We're going to talk about the system design and Google Maps. We're going to start out by talking about the high-level system design and the main workflow between the user and the system. We'll talk about the map rendering, the navigation service, the location service, and other components of the system. Then we're going to drill down into those components in more details and talk about the navigation service and how we can find the most optimal route between point A and point B. We'll talk about the map representation as a graph, and then graph split into the different segments and how we can perform different algorithms on a lot of segments. And then in the end, we'll talk about the final system design and drill down into the components in more details, talk about the trade-offs and different techniques that we apply. With that, let's get to the video. Google Maps is a massive system, so before tackling this question, we'll need to reduce the scope to the main workflows and high-level design, and that's what we're going to start with. So as you can see on this diagram, this would be our high-level representation and the main components of the system. We can go from the bottom up. So first thing first, as you open a Google Map on your phone, for instance, you see an image of the map, and that can be just a default image. And then as you turn on your GPS or you zoom in on your map, you see in more detail representation of the map. So the way this is going to work is by your phone downloading images with lower or higher resolution of the map from the server. In our case, there would be a CDN where all those images are located. They are pre-static or they are not updated very often, so we can just host them as static files on the CDN. If you're not familiar with what CDN is, it's a content delivery network, and if you want to learn more about it, click the link above. I have a dedicated video on how to design a CDN and how it works. CDN has to be backed by a service that would provide all the data and information, and in our case, it would be a geocoding service. So this service would be a spatial index or representation of the map as a set of segments. And in our case, you would use a GeoHash where we would take the map and split it into multiple grids and then keep breaking down those grids into more grids recursively until we get to the lowest resolution possible or that we want to support. I talk more about it in my proximity service videos if you want to learn more about how the GeoHash is implemented or how else you can represent the map. Go and check out my proximity service video where I talk specifically about the GeoHash and quad tree representation of the map. Now back to our high-level design. So as you can see, the geocoding service would implement that spatial index that would be stored and cached in the Redis database. So every single time where we would need to understand in what segment the specification exists, we would be able to query the geocoding service and get it back. So that's how we would be able to open the map and then zoom in and zoom out and see all the locations of the map. Now let's say we want to go somewhere. So we either search for the nearest coffee shops or we put a specific address in the map and try to find a route. So the following is happening behind this scene. First, we go to the area search service, and this is the service that is responsible for translating a specific location. We're going to go, for instance, an address of the coffee shop to a latitude and longitude. Or if we look for the coffee shops in the area, then it can be a proximity search implemented where we would find the closest coffee shop to where we are located and then return multiple of them on the map. And then we would choose the specific place we want to go to and click the directions button in our app. So behind the scene, we would either use the proximity search to find all the places, or we would use an Elasticsearch to find a specific name of the place where we want to go. And then we would return back to the client the place, name, and details, as well as the latitude and the longitude. Now the user has the source and destinations and the coordinates on where we want to go. So the next step, we click on the direction button and we get the route to the place we want to go generated and returned back to us. So this is how it's happening. We send our coordinates to the route planner service. And that's the service that would first call the geocoding service and get the segments for the source location and the destination location based on the coordinates. As well as these two segments, we would also want to get an area between these two locations. So likely we would compute the aerial distance between the source and destination, and then use this distance as a radius from the source and destination to retrieve more segments that would likely be used for our route generation. So once we know those segments, next thing we do, we would call the segment graph service. And that is the service that would have a graph representation for every single segment. So we would get a list of graphs for every single segment between the source and destination. Now we can use these small graphs to build a bigger one and find the shortest path from the source to destination. Now, as we have a list of routes, we want to check the current state of the roads. So we would use the live traffic service that would give us the information about the recent incidents or jams or whatever else is happening or might be happening on the routes that we've just computed. And if there are any issues, we would just remove some of the routes that are less efficient and keep only those that are the most optimal to get from point A to point B. Once we have that, we also want to compare that route with the historical ETA data. Because now, as we have the most efficient, as of now, we want to check whether it's as efficient as it was yesterday and the day before yesterday at the same time. And if it's not, that it could be either because of the accidents on the roads or some delays. And we would want to either update historical ETA because this is the most efficient route at the moment, which means that historical data might need to be altered. And if the route is slower than usual, we would want to likely highlight it in red and tell the user that there is an incident or some small delay on the route. Once we have all of this, we return it back to the user. Now the user has the most optimal route or perhaps multiple that one can select based on the preferences. And as we drive, we would want to keep sending our location for multiple purposes. The first one, we want to make sure that our live traffic is getting updated with our own data. So if we slow down on the way, then we know that there is an incident, and as all the users send their locations, we'll always know what roads are slower than usual, as well as we want to make sure that we are rerouted in case there is a jam or some slowdown on the way. So this is where the navigation service would play a role, and in case our ETA would be altered to this by the specific threshold based on the live traffic events or something else, we would get our route recomputed and get the more efficient one. And this workflow would be implemented at the top of the diagram. As you can see, we are sending a push updates to the server, and then those updates would be synchronous. They would go through the Kafka to our service, them stored, and the historical data, as well as the live traffic service that would use all those updates from different users to keep track of the current road conditions. Okay, let's switch gear a little bit and talk about how we would represent the global map as a graph data structure. As you know, graph consists of the vertices and edges. And in our case, roads would be edges and intersections would be vertices. Our graph would be bidirectional, which means it wouldn't have a specific direction. So if you can get from point A to point B, it means you can get from point B to point A because most of the roads have multiple lanes. And also we would have a weighted graph because every single edge would have weight on top of it. And weight would represent the ETA, the average speed, the distance. We would have a specific metadata assigned to every single edge that would represent different parameters of that specific road. So let's say we have a graph and we need to find the most optimal route from point A to point B. Of course, we can use the Dijkstra's algorithm to find the shortest path from point A to point B, but likely it would take a long time because we have a huge graph and we would need to traverse a lot of roads and vertices to get there. Especially if it's a long route like from New York to LA. There are hundreds of thousands of different roads, intersections that we would need to traverse to find that optimal route. So that wouldn't be efficient and impossible to get instantly as we see on our application. So how do we deal with this? First, we spoke already about using a GeoHash index. So what it does, it splits through Earth into the segments. Now we just need to adapt the idea of using graphs into this segment model. Now every segment would have a separate independent graph that would consist of all the roads and intersections in the area. So this way, if the source and destination located in the same segment, we still apply the Dijkstra's or A-star algorithm and find that most optimal location inside the same segment. But what if our destination and source are in the different segments. In this case, we would use a notion of the exit vertices. So as you can see on this diagram, for instance, we have a small graph inside the segment, and then this graph has exit vertices that are adjacent between the other segments. So we can traverse from one micrograph to the other one in the other segment using these exit vertices. And now if we zoom out for a second and think about how they would represent a bigger territories or bigger segments, then we can think about just utilizing purely exit nodes and use them to create a bigger graph. So you can see on this diagram, for instance, all the inner segment nodes are ignored, and we only use exit nodes to build a graph that has less vertices and connects multiple segments between each other. Using this approach of converting the small graphs into the exit nodes and then build a graph of a lower dimension lines up with our model that we use for the GeoHash, where the world is split into the segments, and then all the segments are recursively split down until it gives to the highest possible resolution. And as we traverse through the segment in the GeoHash, going to the higher dimension or lower dimension, we can also traverse through the graph representation and convert the micrographs into the exit node graphs to be able to build a graph of the lower or higher dimension. But to be able to use this model and be able to traverse between different dimensions of the graphs, we need to know the shortest distance in the micrograph from any point on the map to the exit node. So all of these distances would need to be pre-computed ahead of time, which means that if we pick on the map randomly, from that specific point, we would have a pre-computed shortest direction to an exit node. And then once we are on the exit node in the graph, we can use that to zoom out and use only exit nodes to traverse and go in the direction of the destination. This approach gives us a performance boost because now we don't need to compute all the possible ways at the highest dimension of the graph using all the roads. All we need to do is to get the shortest path from the source to an exit node. And then from the exit node, we can always zoom out and use one of the exit nodes to find the path to the destination. And in case we go from New York to LA, we're not going to traverse all the local roads or small vertices and edges in the higher dimension graph. All we need to do is to find a shortest route from our current location to the exit node, and that use that exit node to find the shortest route to the other exit node at the higher level of the segment until we get to the resolution where the shortest path from New York to LA will be a highway. The whole idea of grouping the graphs and the segments based on the idea on how we represent the map as a geohash. And I talk about it in more details in my video about the proximity service. So go check that video if you don't really follow on what I mean by different dimension graphs and segments. And now as we came up with the way of going from the higher dimension graphs to the lower dimension as we increase the distance between the locations, let's talk about the navigation service and why you would use one roads over the other roads. So the way the navigation service and the ETA is computed is mostly based on the quickest routes and the most optimal route that is pre-computed. Meaning that if there is a route from New York to LA using the highway, likely we're not going to do any pre-computation or comparison of the routes that go through the local roads, because those would definitely going to be slower, and it just makes no sense for us to even try that. The navigation service would be optimized to look for the most optimal route based on pre-computed route. And as a lot of routes from the nodes inside the micrograph to the exit nodes would be pre-computed, then we would be able to use all that cached route information to go from the higher dimension to the lower dimension graph. Now let's circle back to our high-level system design diagram and talk about some of the components in more depth. So first of all, as we already spoke about the main workflow, we have a service called segment graph service that stores a mapping between a segment ID and a micrograph that is located inside that segment. To store micrographs of different dimension, we would need a Q-value data store where the ID would be a segment ID and the value would be a micrograph. And the graph is usually represented as an adjacency list. So we can just store it as a binary, as a value in our database, because we never need a partial micrograph. If we need a graph, it's a graph in the specific segment, and key value database going to work just fine in this situation. If we look at our historical ETA data service, this is pretty much very similar idea here, that we can use a key value data store where the key would be a source of destination and the value could be a single or multiple routes for the specific direction. Since it's a historical database, then likely every single time that the route finder computes the most optimal path and return it to the user, we would also store this route with a timestamp because we want to know what is the average ETA from point A to point B at this specific time. So as we compute a route for a user right now, we know the historical ETA and we can say whether it's slow or fast or average. So this way, the database would like to have source, destination, timestamp, and then a list of routes. Also, as we use the app, we need to keep sending our current location to the server, just so first we can keep the route up to date and get it recomputed if it gets slower. At the same time, we use this information for all the analytic purposes, right? And there are a lot of different things we can compute with the user data, starting from the live traffic service, ending with creation of the new segments or new roads, updating the already predefined graphs with new perhaps rows and intersections that get created all the time around the world. And if you think about the analytics specifically, there are a bunch of different use cases. As you can see here in the diagram, the current location go through the Kafka, and then based on different Spark perhaps or streaming and batch jobs, we would be able to find new roads. We would be able to determine different hotspots or traffic jams on the road, and then update our live traffic service. At the same time, like UT prediction, user similarity, vehicle classification, a lot of other stuff we can compute out of it. One more thing I want to talk about is how we find that most optimal route, because this is the most complex feature in the whole system. And the key here is that as our route finder service receives source and destination, we now have to retrieve a list of segments from the geocoding service, and then later on a list of graphs. The key here is to understand what segments we need. Because if we look for a distance from New York to LA, we don't need small segments. We don't need high resolution segments. We need the large segments that cover the whole United States, just so we can use those edge nodes and find that shortest, most optimal path. And the trick here is that what kind of resolution segments we retrieve. And multiple options that can be used are, for instance, the route finder can retrieve multiple dimensions of the segments. For instance, it can retrieve 5 large segments, and then it can retrieve 100 smaller segments, 1,000 even smaller segments, and compute shortest route across multiple dimensions. And then check what is the most optimal route that we need to use. And in this case, the low resolution big segments would compute like with the route based on the highways. So this is where the whole trick is, having the routes pre-computed across different dimensions, and then based on the source and destination, find most optimal routes. But if we can't, or a second tool on time, we can just always check historical ETA data and get the most optimal route from there. All right, I think I covered all I wanted for this video. I hope you found this video useful. If you liked it, make sure you click the subscribe button and like the video. I really appreciate it, and I'll see you in the next one. Bye.